So we're getting ready for the final, and I wanted to do a little bit of a review over this vector field, or this vector analysis chapter. Now, we started off talking about vector fields and, just the basics. We've got a vector field here defined to be yx. And let me write it a little better. It's a vector field, two-dimensional, and it's defined this way. So, for example, if we have the point 2, 3, and we want to see, well, what vector is that? Well, it says take the y-coordinate, put it in the first position, and the x-coordinate, put it in the second. So we would get this vector. Now, how to represent that? Normally, when we represent a vector function output, we would start at the origin, and this would be the terminal point. But that's not the way we graph these vector field vectors. What I'm going to do is I'm going to go over here 1, 2, and up 3. I go to the point. I go to this point, 2, 3, and then I treat that like the origin. And from there, I'm going to go 3 to the right and up 2. So I go over 1, 2, 3, and up 2, and there's my vector there. So that's the way we would, plot the output from a vector field. Now, the next thing we have down here is we have the divergence. So, in other words, notice that this is going to be partial with respect to x, partial with respect to y, dot, if this here is a two-dimensional, so it would be mn. And the way we interpret that, remember, is partial m with respect to x plus partial n with respect to y. So for our particular problem here, we've got the partial with respect to x, partial with respect to y, and this is the operator. We're just going to differentiate. So we've got y and x, and of course that's just going to be 0. See, partial of y with respect to x, well, that's 0. Partial of x with respect to y, that's 0. Now, next we want to apply the test for convergence. So, see, we've got these various things. We're just learning to work with vector fields. So with this two-dimensional vector, now, and by the way, for this divergence, if we had a three-dimensional vector, it would go like this. It would be partial with respect to x, partial with respect to y, and partial with respect to z. And then we would dot m, n, and p. And we would take the derivative with respect to x of m, derivative with respect to y of n, and the derivative with respect to z of p, and add those together. So that's if we had 3 dimensions. Now, if we go over and we want to test for convergence, so one of the ways, the way we test it for convergence is this. We said, okay, let's suppose, and we'll do the two-dimensional case here. We've got xy, and that's m and n. Now, the way we test it for conservative, way we test, not for, I may have said convergence, the way we test to see if it's conservative is we set up this little thing to help us to remember. Partial with respect to x, partial with respect to y, and then here's m and n. And we do like we do the determinant. We cross, just like we were working with the determinant, the partial of n with respect to x minus the partial of m with respect to y. And if that equals 0, then we have a conservative vector field. Okay, so that's how we test to see if a vector field is conservative. Now, that's if it's 2 dimensions. Now, if it's 3 dimensions, let's suppose we've got 3 dimensions here, and we've got m, n, and p. If we have this, then we run it through this. We have I, j, k, and then partial with respect to x, partial with respect to y, and partial with respect to z, and then we have m, n, and p. And we go through the process like we're finding the determinant or the cross product. Same process. And the way we would write this, we talk about this being the curl, and we write it this way. This little cross product here, like this. That's the way we write it to tell us, yeah, we're looking for the curl. Now, another way we could write that is we could say CURL and F, like that. So the curl of F, or this is the cooler way to write it. All the cool kids write it this way. And it's just like up here for the divergence. We write this as dot F. So we've got the divergence and we've got the curl. Okay? Both things. So in this first section of this chapter, we were concerned about what is a vector field, and then in particular, the curl and the divergence, and how to determine if a vector field is conservative. Okay? And we tell if it's conservative by looking at the curl. Now we want to find the potential function of f of xy. Now, we have decided that this vector field up here is conservative. So, and we did that because, this equals 0. In other words, this is true. The partial of n with respect to y is equal to the partial of m with respect to x. Well, actually, I got that backwards, didn't I? The partial of n with respect to x is equal to the partial of m with respect to y. And both of those are equal to, the partial of n with respect to x is 1, and the partial of m with respect to y is 1. So 1 equals 1. So that's a conservative vector field. So we want to find the potential function. When we say something is a conservative vector field, that means that the gradient of some function is equal to that, creates that vector field. And we refer to that function, that f, as the potential function. So I want to find the potential function. So I've got the vector field here. And the vector field is yx. So let me just integrate. I'll take f, and I want to integrate y with respect to x. And that gives me xy plus some function of y. Now I could do it again. I could say, well, let me try it again. I want to find out what this function of y is. So I'm going to integrate the y with regard to, with respect to, I'll integrate the x with respect to y here. So I'll get xy plus, h of x. Well, it's pretty clear that the function that we're looking for is xy, because the partial of xy with respect to x is y, and the partial of xy with respect to x is so look here. Okay. Here's what we're saying. The partial with respect to x is y, and notice, that's right there. And the partial with respect to x, the partial with respect to y is x, and that's right there. So we have found the potential function. Okay, now that we have the potential function, let's see what's next. Okay, we want to evaluate this line integral for a vector field for this curve, this piecewise smooth curve, going from 1, 1 to 2, 4. Now, we know this is a potential function. We know that this is a conservative vector field. Since it's a conservative vector field, we do not care what path we take to go from 1, 1 to 2, 4. We don't care because it's conservative. So here's what we've got. We've got xy, and we're going from 1, 1 to 2, 4. So this would just be, I just plug this in, 2 times 4 minus 1 times 1. And that's all there is to it. We start from the lowest point, go up to, the starting point is here, the ending point is here. And we would get 8 minus 1, which is 7. And that's it. Okay, now there we have a conservative vector field. And we can do this. This is the fundamental theorem of calculus. Now, let's go down here. Now, we have this line integral here, and this line integral does not involve a vector field. It's a scalar. It involves a scalar function. Now, remember, with the scalar function, we're going to parametricize it. We're going to find a parametric expression for these curves. I've got C1 here and C2 here. And we remember that d little s is equal to the square root of x prime squared plus y prime squared dt. Now this is for two-dimensional. If it were three-dimensional, I would have the z prime squared, where we have the r, is equal to x of t and y of t. Okay. So we're trying to find a path. Okay. So let's see if we can figure that out. Now, and by the way, ds, really all that is the magnitude of r prime of t. That's what that is, dt. So you could think of it that way as well. But we've got this vector, this path, vector valued function. And I need to choose C1. I need to choose a path for C1. Well, C1, I could just do this. R1 is equal to t and t squared. Yeah, that will work. See? And I'll have t going from 0 to 1. Now, while I'm at it, get C2. Now, I have to be careful here because C2, you're going from 1, 1 to 0, 0. So you're going from right to left. So you have to really be careful there. So let's see here. Maybe I'll do this. 1 minus t and 1 minus, and then I'll just do, 1 minus t for both of them, right? So if t goes from 0 to 1, let's see what I got. If I put a 0 in here, I get 1, 1. If I put a 1 in here, I get 0, 0. Ah, that will work. So let's see here what we've got. Now, so when I calculate this, this is going to be for C1 and for C2. So I've got to do both of those. So let's see what we've got here. As far as C1 goes, I need to get the ds. So here I go. It's going to be the square root of the derivative of t is 1. So this is 1 squared plus 2t squared. That's 4, or 2t. That's 4t squared. See? I just took the derivative. I got 1, 2t, and I squared them. And then here is my integral. I'm going to go from 0 to 1. In place of x, I'm going to put t. And then I've got 1 plus 4t squared dt. That will be the C1. And you can use substitution. Okay, I'll just set that up. But you can use substitution and evaluate that integral. Then we've got C2. Okay, so this is still going to be 0 to 1. And for x now, I've got 1 minus t. See? Just put 1 minus t. And then I've got the derivative. So the derivative, this is negative 1 squared. Negative 1 squared. So this is going to be the integral from 0 to 1, 1 minus t times the square root of 2 dt. And you would integrate that. So you would integrate this one and put them together. And that would give you what you're looking for. Okay, now let's go down here. Now, here we've got a line integral. And this line integral is involving a vector field. Okay? So, and I've given you here the path. Okay? So we're integrating along this path for this vector field. Okay? So let's see if we can get this set up here. Now, I've got x, y. So let's see what, in place of x, I'm going to put a t. And in place of y, I'm going to put a t squared. See? In place of x, I put t. And in place of z, I put 2t. Then I've got y and z. Okay, there we go. Now I'm going to put in here the derivative. So this right here is going to be 1, 2t, and 2 dt. And I'm going from 0 to 1. See? So you're going to do the dot product. So let's see what we get here. We get 0 to 1. And this is going to be t cubed times 1. That's t cubed. Okay, so this times this. And then this is 2t squared times 2t. That's going to be 4t cubed, right? 2t squared times 2t, that's 4t cubed. And then plus, this one right here is 2t cubed times 2, that's 4t cubed. Times dt. Okay, so let's see what we got here. We got 0 to 1, and this is, man, there's a lot of t cubes there. It's 9t cubed dt. There. So you've got a nice, easy integral there that you can work. Yeah, so that's easy. Okay, now let's look at this one. Now this one, you see this little circle here on the integral, that indicates, you've got a closed boundary here. You've got a closed region for this line integral. And you're thinking, I bet I'll use Green's theorem on this one. Now, for this integral, if you're dealing with a conservative vector field, then that means that integral is going to be 0. Okay? So that's the deal with these conservative vector fields. You've got the fundamental theorem of calculus. And then you also know, well, if you have a closed curve, your integral is going to be 0. Now, I'm thinking this one's not closed, so I'm going to use Green's theorem. As it says, use Green's theorem. Okay, so use Green's theorem. So here we go. Now remember Green's theorem. So we got to do this. We got to find, we're going to integrate over this region. We have partial n with respect to x minus partial m with respect to y. So we got to get these parts. Now this vector field up here, if we unravel it, we've got 2xy, comma, x plus y. There, that's the vector field. So now let's see what we've got here. We've got the partial of n with respect to x. Well, that's just 1. Partial of n with respect to x. The partial of m with respect to y, well, that is going to be 2x. So it looks like we've got us an integral here that goes like this. 1 minus 2x. Yeah, that's it. Okay, now we've got to determine our boundaries. So let's see here. Let's look down here on the XY plane. Here's X and here's Y. And here's a curve here. We've got 1 minus x squared there. And we've got y equals 0. So it looks like this is our boundary right here, inside, above the x-axis and inside this pink curve here. So I guess what I'll do is I will integrate with respect to x first. Or actually, let me integrate with respect to y first. Okay. Let me integrate with respect to y. And I will go from 0 to 1 minus x squared. Okay. So for whatever x, I'm going to go from 0 to 1 minus x squared. And then the x is going to go from negative 1 to 1. So that would be dx. So working that out, you would get your solution. Okay. Okay, now so that's how we would use Green's theorem on that. Now let's go down here, and we've got this sphere, x squared plus y squared plus z squared equals rho squared. And what we want to do is we want to, come up with a parametric surface. So here we go. Let's see here. We've got r, phi, and theta. So let's see what we've got. Now, we know what these look like. We're going to have rho. For the x-coordinate, we're going to have rho sine phi cosine theta. Okay? And then for the x, we have rho sine phi sine theta. And then for z, we have just rho cosine phi. Yeah, there it goes. Okay, now we want to find the partial with respect to phi and the partial with respect to theta. So here's the partial with respect to phi. So let's see here. Well, let's look at the parts here. So this is going to be rho cosine phi cosine theta. And then rho cosine phi sine theta. And then negative rho sine phi. Now let's look at the partial with respect to theta. That's going to be, okay, here we go. Negative rho sine phi sine theta. And then rho sine phi cosine theta. And then 0 here. There's no theta in there. Now, this down here, so now down here we're just asked to find the surface area of a general sphere using the cross product. Now, what that calls for is to use the formula for surface area when you have a parametric surface. So, in other words, you have something like this, just the general form, and you have to remember that that's going to be, you change it over to a double integral, and we're going to do the partial with respect to phi cross the partial with respect to theta dA, where dA is the area. Okay, so in this case it's going to be du d phi. I mean, not du, d phi d theta. So let's see what this would look like. Let's think about our double integral here, and we've got this cross product. Now, I think what I want to do is I want to integrate with respect to phi first. Now phi, think about a sphere here. It's going to start off at 0 and go to pi. Okay, so think of phi. Phi starts at 0, that's like at 90 degrees up there, straight up. It's on the z-axis, and as it rotates down, the angle made with the z-axis goes all the way to pi. And then we talk about theta, and theta is going to go from 0 to 2 pi. So all you would do is find the cross product of these things that we just looked at in part B, and then you would set up your double integral. And that's all you do on those. Okay, now let's go down to another surface integral. Okay, so we've got a surface integral here where we're going to evaluate a surface integral involving a scalar function. Okay, so let's see how this would look. Now remember, d big S is equal to the square root of partial z with respect to x plus partial z with respect to y plus 1. And that is each one of these are squared. So let me put a square in there. Okay. And then dA. Yeah. So remember, this is how we can interpret. Now if we were in a parametric form, it would be the cross product. Like if we were in parametric form, it would be the cross product of u partial r with respect to u cross partial with respect to v dA. That's if we were in the parametric form. Okay, so if we were dealing with a parametric surface, but we're not here. So here's what I need to do. Now, I've got this double integral. I've got x, y, and then here, look what I've got. I've got -1 squared plus -1 squared. So the partial with respect to x squared, partial with respect to y, and then plus 1. And then dA. Okay. Now normally, we've got... Okay, so the packet begins with this part. So normally, if this were x, y, and z, I would need to substitute the z with 3 minus x minus y. But we don't have a z there, so we're good. So here's what we've got. We've got the square root of 3, and now we've got xy, and I'm projecting down here on the xy plane. Okay? So I've got x plus y equals 3. So I've got that, x plus y equals 3. Now, we got to integrate. I'll integrate with respect to x first. Or with respect to y first. I'll integrate with respect to y first. We're going to go from 0 to 3 minus x. See? And then integrate with respect to x, and I'm going to go from 0 to 3. And there's our double integral there. That's just a simple double integral. Okay, now let's look at number 7. Now, so this was a surface integral with a scalar function. Now we have a surface integral with a vector field. So let's see how we're going to do. Now with these ones, what I do is I get a level surface. Okay, I want my orientation to be outward from the graph. In other words, I do this. I bring everything over with the z. Okay, so there's my level surface. And the reason I do that is because I want to get the gradient. I want to get a vector that's orthogonal to that surface. So I can do that. I can get the gradient. So this is going to be partial with respect to x, partial with respect to y, and partial with respect to z. Okay? So I got that from that surface. Now, here's the way I'm going to set this up. I set this integral up this way. I take the vector field, and I dot product that with the gradient. And then A, and I project that down. Well, I'm not entirely finished. I'm going to project this down into the XY plane. So I'm not entirely finished. Let me just go ahead and do some of this work first. I'm going to project down into the XY plane, and I've got 3z minus 4 plus y. Okay, there's what I have. I just did the dot product. Now, I want to limit the values to what's on this surface. In other words, when I plug in numbers into my vector field, I'm limiting my z values. I'm limiting to what's on this surface. Z equals 1 minus x minus y. So I'm going to do this. I'm going to rewrite this z as 1 minus x minus y. Okay? And now I can project down into the XY plane. Let me go ahead and clean this up a little bit. So I have negative 1, see, 3 minus 4. And then I have negative 3x minus 3y, so plus 1, that's minus 2y. Okay, there we go. And now I can talk about what I'm going to integrate. I guess I'll integrate with respect to y first, and then with respect to x. And I'm projecting down here on the xy plane. I've got x plus y equals 1. So x plus y equals 1. So y is going from 0 to 1 minus x, and then I'm going from 0 to 1 for the x. And that integral will give you what you're looking for. So you integrate over that, and you'll get that's the setup. And I'm assuming we can handle the double integrals there okay. So I'm just trying to, for time's sake, just trying to get these set up. But let me know if you have questions about those. Now, next we want to use the divergence theorem to evaluate this surface integral. So what we're going to do then is we're going to write this as a triple integral, okay? And inside here is going to be the divergence, okay? So we'll have the divergence in ds. Actually, I got ahead of myself here. So we have this. So we have this surface integral. Okay. And what the divergence theorem says is we can rewrite this as a triple integral. Okay, over some solid, where we have the divergence times the volume. In other words, so let's see how we would set this up. In other words, this is a way that we can deal with this surface integral with a triple integral. So let's see how this works. We have the divergence. So let's get the divergence first of all. Okay. So partial with respect to x, partial plus partial with respect to y, plus partial with respect to z. Okay. So that's the divergence. So let's see what we've got here. We've got this triple integral. We've got this divergence. 2x plus 2y plus 2z. Now what I need to do is, well, this is the setup so far. Now what I need to do is just integrate. Now notice the divergence theorem applies here because we've got this closed surface, right? X equals 0, x equals a, y equals 0, y equals a, z equals 0, z equals a. So you've got this cube. You're integrating over this cube. Now you could deal with this integral by doing surface at a time, calculating the surface integral for each of those surfaces. But this theorem gives us a way that we can get around that. So you can see this would be a lengthy process if we didn't have divergence theorem. So let's see what we've got here now. We've got the triple integral. We've got 2x plus 2y plus 2z. And I guess I will integrate with respect to x first, go 0 to a. Then with respect to y, 0 to a. Respect to z, 0 to a. And that will give us what we're looking for. That will give us the answer to this problem. Okay, so now all you have to do is work through that triple integral. Okay, looks like we're on the last one here where we have Stoke's theorem. And Stoke's theorem is going to show us a relationship between a line integral with a vector field and a surface integral. So in fact, we have this line integral where we have C C and then F dot dr. And Stoke's theorem tells us this, that we could rewrite that as a surface integral where we have the curl dot in ds, like this. So in other words, we're able to rewrite this as a surface integral. So it's just like solving a surface integral problem, except instead of f dot n ds, we have the curl of f dot n ds. So I need to find the curl. So here I go. The curl, it's going to be like finding the determinant or the cross product. Okay, so I've got, partial with respect to x, partial with respect to y, partial with respect to z, and then I've got z squared, 2x, and y squared. Okay, there I have it. Okay, now, so let's see what this is going to give us. Now, I want to make sure I got it. Z squared, 2x, y squared. Okay. Okay, so I've got partial with respect to y squared, or partial of y squared, partial with respect to y. This is going to be 2y. Okay, just 2y. Now, I'm ready for the middle one. So this is going to be 2z. Let's see here. Yeah. And then the last one, it's going to be 2. Yeah, just 2. There it goes. So there is my curl. And now we're just working along here just like before. So now I've got my gradient. I'm going to find the gradient. So I'm going to get a level surface here. And I've got z plus x squared plus y squared minus 1. And I get my gradient. And that's going to be 2x, 2y, and 1. Then I dot product. I dot product these two little fellas, 2x, 2y, and 1. And let's see what I get now. I get 4xy. Whoops, it's not a vector. 4xy plus 4yz plus 2. Yeah, that's it. Okay, now we're not quite ready to go to the integral. We've got 4xy plus 4yz, 1 minus x squared minus y squared. You always do this with these surface integrals. You replace, whatever. this is z equals 1 minus x squared minus y squared. You replace the z with what it equals. In other words, we're projecting down into the xy plane, so we're going to replace the z's. Okay, you can do these different ways, remember. So plus 2. Yeah. So let's see what we've got now. We've got 4xy plus 4y minus 4x squared y minus 4y cubed plus 2. Now we're ready for our integral. So we write this, we've got our double integral here, and we'll write this as, put everything in here, 4xy plus 4y minus 4x squared y minus 4y cubed plus 2. And I'm going to integrate, I guess I'll integrate with respect to y first. And remember, we're down on the xy plane, so we've got z is equal to 1 minus x squared minus y squared. If z is 0, we've got x squared plus y squared equals 1. So I'm going to integrate from negative 1 minus x squared to 1 minus x squared. Yeah. See, because it's a circle. And then I'll go from negative 1 to 1 for the x. And that will give you what you're looking for. Okay, so just integrating this monster is all you need to do. Now, I think that's all of those.